So hello everyone and welcome to this supplementary video to our course Reliable Simulation in the Mechanics of Materials and Structure. Today I will talk about the second and last example in connection with coupled problems, namely the fluid structure interaction. I will talk first about the solid subdomain as a separate problem, and I will give an example in connection with linear elasticity. Then I will talk about the fluid subdomain, where I will give an example about the flow of incompressible fluid. I will talk then about the coupling interface between the subdomains and some general comments about solving this fluid structure interaction problem. So first, the problem of fluid structure interaction belongs in general to what we call the surface coupled problem, because we have a clear interface between, as we see in this picture, we have a clear interface between the solid subdomain and some kind of fluid subdomain. Each of these subdomains could behave differently, but they interact across this interface. Therefore, because they interact, because they behave from mechanical point of view in different way, they might be governed by different equations, and each subdomain can be covered, can be subjected also to different conditions. And an interface condition govern, as I said, the relationship between these two subdomains. In case of fluid structure interaction, we need a mechanical description of the solid subdomain, of the fluid subdomain, which is in itself. So if we take the fluid alone, it's a volume coupled problem. And then if we look at the solid fluid interaction, then it is a surface coupled problem. Therefore, we need to look at the coupling interface in a specific way. So this problem in general, as I said, it includes a volume coupled problem for the fluid itself. But if we look at the interaction, then we have a surface coupled problem. And we will see this in the context of this lecture. So for the structure subdomain, so assume that the structure is subjected to small deformations. So we're going to take simple setup of our mechanical description. And in this case, as it is a solid material, then we have one primary variable, which is maybe the displacement U. For this simple problem, we have seen if we have only mechanical effects, no temperature, and so on, then we need only one balance equation, which is the linear momentum balance. In general, it can be given in this form. So we have on the left-hand side the inertia term, so the density multiplied by the acceleration. And then on the on the right-hand side, we have the divergence of sigma, which is our stress tensor, plus rho b, which is our body force. If we say that we have quasi-static setup, then we can ignore or neglect the inertia term. And if we say that we have a linear elastic problem, then this constitutive model can be considered. This includes two material parameters, which might be the Lamé constants, nu and lambda, which we need to figure this out. If we write this in abstract way, then we have the stress and the strain, and between them we have the elasticity tensor. In three-dimensional configuration, it would be a fourth order tensor. This solid problem, or the solid subdomain alone, it's not a coupled problem, it's a non-coupled problem, because we have one equation, we have one variable, so it's non-coupled problem, and this makes the solution easy to implement. I will give you here an example. So assume that we have such a structure, which is maybe a pipe. It's a solid material made of steel, and we would like to compute the displacement or the deformation of this pipe, and also the stresses, which result from a kind of internal pressure. And this internal pressure, it comes from some kind of fluid which is injected inside this pipe and causing this pressure, which is uniformly distributed. So the pressure it's always normal to the surface. And I use in the solution of this problem finite element method. I use our software, which you are using also in the exercises, the FlexPDE. And these are the material parameters. They are connected with steel, some kind of steel, which has an elasticity modulus of 200 gigapascal. Nu or Poisson ratio is 0.3. and assume we have a small strain, so we have a linearized strain tensor and linear elasticity, so which means we have really a simple setup of the problem. So in this case, we consider the effect of the fluid through the pressure at the interface. So we solve the solid independent of the fluid in this case. And you see here we have the displacement. It is a result of the displacement in x direction and y direction. And it shows that we have maximum displacement at from the inside, so at the inner side of this tube, and less from the outside. And then if we look at the stresses, for instance, the stresses in y direction, we see we have this contour plot of this. If we take a cut for 1, 2, or if we measure the stresses along this line, then we have this curve. It's clear here at this point that the stresses are maximum at the inside and minimum at the outside. It means if we keep increasing the pressure inside this tube, we might have at some point some crack, which will start from inside, like from this point or from this point. Of course, we need also to consider the stress in y direction, in x direction, and the shear stress. And then usually if in the finite element code, if you are using, for instance, abacus, you compute the von Mises stress, which includes all the information about the or mainly there is a critical shear stress, and then we compare this with the primitive one with the limit shear stress, and then we see if we have a crack or not. But this is beyond the scope of this lecture, so we just visualize the stress here, and this is our first subdomain. Again, this is non-coupled problem if we look at the solid alone. But if we look at the fluid, or if we look at the solid-fluid interaction, then we have a couple. Now, let's move to the second subdomain, so the fluid subdomain. Let's, for simplicity, consider the case of incompressible fluid. So we will have then the incompressible Navier-Stokes equation. If we say that we have also quasi-static, so we have a flow which is very slow. And then we can have some equations to describe the coupled problem. We could have first the mass balance and the linear momentum balance, which are the two equations which are needed then to describe the behavior of our system. In this case, the primary variables are the fluid velocity and the fluid pressure. So we have two primary variables, which is shows us directly that we have a coupled problem, because in this case we would need more than one equation. In this case, if we now talk a little bit about the equation, so more details, we have the conservation of mass, or it's called mass balance, or some people call this also the continuity equation. So if we assume that our fluid is composite of one component, so sometimes we consider the flow of two fluids at the same time, which makes it a bit more complicated. Like if we have a flow of water and oil together, but now we have one fluid. So the conservation of mass in general can be given in this equation. So we have the time derivative of the fluid density plus divergence of rho f. So rho f, divergence of rho f multiplied by Vf. So again, the density multiplied by the fluid velocity equals to 0. This is a conservation of mass. But now if we say that we have incompressible fluid, it means our fluid density is constant, it's incompressible, which means that the time derivative of the density is equal to 0. And then we have a very simplified equation. It's divergence of rho f Vf equal to 0. This is our first governing equation, which is the fluid, let's say now it's fluid volume balance. We started with the fluid mass balance, but because we have constant density, now it's about the volume balance. Let's say this is what we usually call this equation. Now the second equation, which we'll need it because we have two variables, we have the fluid momentum balance. It can be given in this form in general, which includes the density, as it should be rho f Vf dot, equals to divergence of TF, which is the total stress of our viscous fluid, plus rho F multiplied by B. Now, if we say that we have quasi-static setup, then we have rho Vf dot equals to 0. Now, this total stress is written in terms of the pressure B and fluid viscosity tau, which is like tau minus B identity. Then with tau equals to 2 mu F and then some function df, d function of Vf, because we have incompressible fluid, so we don't have volumetric part in the in tau in the like viscous stress. We have only shear stress due to the viscosity of the fluid, and this can be written as mu F gradient of Vf gradient of Vf transpose. And mu F would be the fluid dynamic viscosity, which is the only parameter related to the fluid which is needed in this treatment. If we look at the equation, we would have at some point divergence of tau. So divergence of tau would be then written in this form for incompressible fluid. We would have mu F divergence gradient of Vf. Let's put this like the definition of the total fluid stress and the assumption of quasi-static in the first equation. Then we will end up with this fluid momentum balance, which is our second governing balance equation. Now for the fluid, we have the volume or mass balance from on the one hand, and then we have the momentum balance on the other hand. It means that we have two equations. We have more than one variable, so we have to deal with a coupled problem. If we want to discuss a little bit the coupled problem of incompressible fluid flow, so consider that we have, as I said, incompressible fluid flowing like slowly through a rigid structure. Now we are like neglecting in this discussion the effect of the structure of the fluid. Then we have to deal with a purely fluid flow problem. If we want to discuss the equation, let's write this equation in a very simple form. So assume we have one-dimensional setup, and then we can replace the divergence and the gradients by these partial derivatives. So we would have mu F multiplied by the second partial derivative of Vf with respect to x, minus partial derivative of b with respect to x, plus rho Fb equal to 0. And for the continuity equation, we would have the partial derivative of Vf equal to 0. As I said, the fluid represents a volume coupled problem because when the fluid flow, you will have at each material point of your domain, we have a pressure field and then we have a velocity field. So it's not like a clear interface between the pressure and the velocity field. So they are really coupled at each material point. Now, if we want to visualize this coupling, we can write the equations in this matrix form. So the system of equation is, if we want to go for monolithic scheme, we can, and we write this in a matrix form. The system of equations is solved in one step and in one strategy, of course, because the two equations are now collected together in which we have a global mass matrix, vector of unknowns, and this force vector. It's clear that our stiffness matrix, it has a 0 here at the diagonal, which makes the solution of this problem complicated, because at some point we need to find the inverse of this stiffness matrix, and this leads to some kind of oscillations in the pressure field, because by the inversion we have to figure out, depending on the way that we are inverting the stiffness matrix, we might have some 0 eigenvalues, and then we have to divide by 0 or by very small values. So this is a differential algebraic equation, which we have this higher order algebraic equation. So because we have 0 here, so we would like to find a solution for this special case. And this 0 comes from the assumption that we have incompressible fluid. So that's why we should keep in mind that if we have compressible fluid, the solution of the equation would be easier, or let's say we would have less numerical challenges or oscillations. Although when we say that our equations are incompressible, the equation seems to be simple, but the solution is not necessarily simpler. So one of the way to like get rid of this zero on the diagonal term of our stiffness matrix is to apply a stabilization scheme which is based on penalty term. In this case, we add a penalty term to the continuity equation or to the mass balance or volume balance to enforce the stiffness matrix to be a full matrix. Particular, we add this alpha multiplied by divergence gradient of P, which is divergence gradient is a Laplace. So we have the Laplace term of pressure multiplied by alpha as a small positive stabilization parameter. And it's clear if we put alpha equal to 0, then we recover the continuity equation, which is connected directly with incompressible fluid. And by considering some value to alpha, we get continuity equation, which is very similar to the one which is considered in case of compressible fluid, simply because the density of the fluid, if we have compressible, it can be simplified as a function of the pressure, and then we will end up with something like this. So as I said, this is called the pressure stabilization scheme or quasi-compressibility scheme. As a fluid in this case behaves like a compressible one, so we add like small compressibility in order to improve the stability. And if we look at the system of equations in some kind of matrix form, then we'll see that we have this is the term which will show up by adding this Laplace term. It's clear when alpha equal to 0, then this term will be here 0. And as I said, this term induces like small errors because it contradicts our assumption of incompressible fluid. However, it will help us to get some stability. In other words, we have to figure out some very small value of alpha so that we have stable solution. At the same time, we should not like apply big value of alpha, or let's say let our fluid behaves very much compressible so that we will get also some wrong solution. Now, assume that we have applied this stabilization scheme and we would like to solve or to use the finite element method to solve this in Navier-Stokes equations, or in the way I present it, they are called actually Stokes equations, especially the momentum balance, simply because you have incompressible viscous fluid flow. And this is a steady state flow in a channel which has this form, so it has this small notch. And then we have a pressure gradient. So on the one side, we apply some value of pressure, B0. On the other side, it's P equal to 0. So we let the fluid flow in certain direction. And we would like to visualize the pressure and the fluid velocity in this domain. Simply, we apply this FlexPD code and we apply this stabilization strategy, which I mentioned here. So we have this pressure field, which looks like this. Now you see that we have pressure at each point of our domain. It's clear now it's not something specific region. So at each material point we have pressure field. Now if we look at the streamlines also, we have velocities at each point of the domain. So we have this interaction between pressure and velocity at each point. And in the middle of this channel we have this because of this notch, the velocity is increasing here, and also we have a little bit non-uniform distribution of the pressure field. If we make a cut here, or we take this section 1, 2, and we look at the velocity, we see according to also to our definitions, we have 0 velocities at the boundary, and the velocity is maximum here in the middle. And this is really the solution of the equation which I presented in the previous slide. Let's go for it. It's exactly the solution of these equations in our software FlexPD, and it shows it's working. So if we change the value of alpha, at some point will not get a solution. If we remove the Laplace term, we will not get any solution from the very beginning. Because of this stiffness matrix, it's showing some 0 eigenvalues. Okay, now we have talked about the solid subdomain and the fluid subdomain, and now let's talk about the interface between these subdomains. So we have the coupling interface. We can apply some kind of logical model which represent this interface. We have on the one hand the solid subdomain with some material property, which is the elasticity modulus. On the other hand, we have the viscosity parameter UF, which is the we have viscous fluid, so we represent this by this dashboard. And then we have the interface. As conditions at the interface, first we have kinematic consistency, in which we say that at each point on the interface, the displacement from the fluid side and the displacement from the solid side is exactly the same, and also the velocities are the same, simply because these points belong to the both domains, so they should have exactly the same values with respect to kinematics. And also we have a kind of equilibrium at the interface. So let's say the sum of forces at the interface or action equal to reaction, because otherwise we would not have a balance. And now if we consider that we have an interface with a specific norm vector n, and how can we compute the traction forces at the interface? You remember from the second lecture, I think, it's simply the sigma multiplied by n, our norm vector, then we get the traction from the solid side, and then we have Tf multiplied by n, which is from the fluid side, and the sum of these forces should be equal to 0 in order to have a balance at the interface. As I will give now some kind of general comments on the solution of the fluid structure interaction. Now, in most of the cases, the solid is solved using the finite element method, whereas the fluid, in most fluid dynamics solvers, they use the finite volume method. Although it's not a must, as you have seen now, I solved also the fluid problem using finite element method. But in some cases, especially if you have turbulent flow, it's much easier to use finite volume methods. This is also beyond the scope of this course. And if we use different strategies for the solid and the fluid, then it is easier for us to use these partition schemes, because then we will solve the solid alone, maybe on different computer, or the fluid also alone, and then we find this coupling interface. We enforce this at each time step, and then we bring this information from the interface back to the subdomains to update the solution of each subdomains in kind of iterative way. And now, in talking about this solution, for simplicity, we take the equations again in one-dimensional setup. First, the solid for the case of quasi-static, and in one-dimensional case, we'd have, in this case, only the elasticity modulus multiplied by, this is the divergence of sigma, then it would be second derivative of u plus rho b equal to 0. And as a traction on the interface, it would be Ts equals to sigma scalar n. And this is our traction vector. Then we have the fluid. It's a coupled problem. As I said, there are two equations in one-dimensional setup. And if we consider this stabilization term, then we have these two equations. Again, the interface would be, as the interface, we have this traction. Tf equals to, this small tf equals to Tf scalar n, and let's say we call this minus t, because it's exactly in the opposite direction as the traction from the solid side. If we write Tf in more detail, then we'd have the derivative of velocity with respect to x and the pressure. Now, in the procedure to solve this like a surface coupled problem, so we consider this is like a general description. So if you go into details, you'll find a lot of specifications, and each software will solve this maybe in some kind of modified way. But this is like a general description. So at each time step, delta t, which is Tn plus 1 minus t. So we consider the traction force from previous time steps. So we start with some kind of known variables or known quantities. either at the boundaries or at the interface. But let's say these are the TNB. We call them previously like a predictor or prediction values. Then we solve the solved problem for this known interactions at the interface and also from the boundary, and then we get some kind of updated displacement. Now we take this updated displacement and then we consider this for the fluid problem. In this case, we solve the fluid problem. We consider this UN plus 1 at the interface. Remember, we have the kinematic consistency, which will be then considered as a kind of Dirichlet boundary condition for the fluid subdomain, Dirichlet, because it's exactly the displacement. Or in this case, we should compute the velocity, because the velocity is unknown for our fluid problem. This is, as I say, at the boundary, and then we solve the fluid problem to compute the velocity and pressure at each point of the domain. And then we update the interface force, because now we have also the fluid velocity, so we can update this depending on the resulting pressure and velocity. And then once we have updated this and we go to step number 2, we replace this predictor by this new value here, and then we compute the solid subdomain and then the fluid subdomain interface and so on. So we keep doing these iterations until we finish the computational solution. This is, as I said, this is a surface coupled problem, but the fluid problem itself is a strongly volume coupled problem. So it's like double coupling in this consideration, and that's why fluid dynamics or computational fluid dynamics problems are still challenging. You will see a lot of research group working on such problems, finding efficient solutions, and they are very important in different fields, especially in aerospace industry, in the design of airplanes, in the design of cars, also how the airflow around the cars, or in buildings, how the wind forces work on buildings and so on. So they are very important problems in different fields. Okay, so with this, I'm at the end of this video. Thank you so much, and we will meet each other on Monday. Thank you.